to everyone. This is Project 2 Steel Structure. I'm speaking on the behalf of Joe Mima Construction Group C, and this is John Berry speaking. So what you're looking at is a schedule of what we'll be presenting today. I'll be presenting a short presentation on the scenario and then going into a connections diagram, or a connection diagram, really a 3D model of the connection. And then I'll go over a brief overview of the hand calculations. We'll go into the Excel solver, and then finally we'll go into the InterCalc file. So let's go ahead and go into the presentation. So here's our Project 2 steel structure. So our project details. Our client wishes to set up a solar parking area on some of his property. You can observe that that little image on the right over here. This is something similar to the solar parking area that our client desires. Here we have a drawing to the exact specifications that we plan on building upon approval. So we have a 16-foot span of solar panel, and then 15-foot span of arc beam, and then that is 12-foot off the ground. And so our parking area was designed to the dimensions just stated, and it includes a W10 by 26 beam along with a hollow structural steel square 6 by 6 by 1/8 thickness column, and it incorporates two fixed connections, one right over here and one right over here. And another thing to note is all of this solar panel, all the weight from the dead load and the live load is going to be felt at this point here at the midspan. I'll talk about it later whenever we get into hand calcs, but one thing that you can start thinking about now. So our loads present, solar panels actually do not weigh a incredible amount. They actually weigh 6 pounds or 7 pounds, excuse me, per foot or per square foot. And then we have the estimated weight of support bracing underneath those solar panels. That would make it necessary to be sturdy enough, and that's at 2 pounds per square foot. And these two are going to be dead loads. And our live load, in considering rain or snow, whatever really live would be, maybe it's some animals, would be 20 pounds per square foot. And here is just a little fun fact on why solar. When you use solar panels to create electricity, there's no greenhouse gas emissions released into the atmosphere, and renewable energy sources like solar account for 18% of electricity generation. So now we'll go into our connection diagram. Let's exit out of this. Here's a diagram of our connection. This was modeled in AutoCAD, and really it's not necessarily a diagram. It's just simply a 3D model. So if I orient it this way, what you're looking at now is you're imagining the column set up right over here behind this connector, and then the beam being attached to this flange right here, and it's attached within the web, and then that beam is just coming right at you through this computer screen. One thing you might notice if I come back to a different orientation, that the holes for the attached to the column are actually bigger than the holes attached to the beam. That's because through the calculations that we did, the column will actually experience most of the moment. The beam, this connection is really going to try to make it an extension of the beam, but really where the real connection is going to be is the connection between the columns and the connector itself. So we'll exit out of this. And now we're going to go into our hand calculations. I'll kind of be brief, I'll kind of be quick about the hand calculations to save time on this video. But I encourage, if there's something that you wanted to look more into, just simply pause the video and look more into it. So here we have our loads present. We talked about that a little bit in our presentation, but here's more detail of it. So like I said earlier, this whole entire solar panel will all be felt at this point at the beam. So this beam will feel all of that live load and dead load in the midspan of the beam. And that's calculated through just multiplying the pounds per square foot by the width of the solar panel, as well as the width of the span. Here we have kind of a setup of a multiple span system, and as you can see in one column, um, the area that that the column will support is 10 feet to the left and 10 feet to the right, so 20-foot width altogether. And so here, by using those dimensions, we have our dead load and live load of 2.9 and 6.4 kips, and we'll be using those for the remainder of the project. So after just some initial study and putting these loads into intercalc as well as the beam span data, I chose a W10 by 26. I also thought about the width of the flange as well as how available some of the variables are in the steel manual. Anything under I think 8 W8, it's harder to find variables, and some variables you would actually have to calculate yourself. So even though with my low loads these beams would pass, it still is wise to do something that would be easier to study as a whole. So we determine the nominal flexural strength, and to do that you have to check for compactness. As you can see, the flange and the web is compact, and then you find your flexural strength. We found it to be 130.416 foot kips. And then we found our maximum bending moment, and our bending moment is going to be at the two edges, because if you know it, if you remember much about fixed connection, it's experiencing a large amount of moment at the edges because of those fixed connections. And we use this formula, PL over 2. That's from table 3-23. So if you're comparing this to your scenario or to your hand calcs, this formula is going to be different because of my specific case of the two fixed connection. Maybe you did a cantilevered beam, maybe you did something different, so just maybe note that. And then comparing that bending moment that we found to be 69.75, we then compared that to the bending moment allowed found from the table, a table in a steel manual, in the steam manual. And so then this beam passes because the bending moment allowed is greater than the bending moment applied. So it passes from bending moment. Now we move on to allowable stress, and going over this, we have applied stress, not allowable stress, applied stress. I want to note that was a mistake on my part, of 30 foot kips, and then we have an allowable stress of 33.6 foot kips. And so our allowable stress is larger than our applied stress. So our beam is passing from that end as well. And finally, we have deflection. This formula, again, is case specific. So it's my specific case of fixed connection. And so using that formula, we have a deflection of 0.00039 inches, which is lower than our L over 360. Now to go to our connections. Here is a diagram, a sketch, if you will, of our measurements for our connections. You have 3 bolts. These bolts will be 3/4 inch bolts, and it'll have 2 2/3 inch spacing between them, and then it'll have 2 inch spacing from that to the edge. And then here is just a dimension from the edge of the column to the middle of the bolts. And this is just to show that the flange is meant to be 6 feet. And then I failed to show the dimensions over here, but that's actually going to be a 1 1/4 inch diameter hole that's going to be drilled into that one to connect it over there. So we just simply wrote down the shear strength for this bolt, the 1/4 inch bolt, S loading, group A, X threads. So simply just wrote that down to put on the top of our list. And then we have our bearing strength of our inner bolts, which would come out to be 10.73. That's hard to see, but that's 10.73. And then our bearing stress from the edge bolts is 6.05. So then we have our shear applied, and so our shear applied is going to be 1.617, and that's going to be greater than our shear our shear strength right over here. So now we solve for our tensile force. So to do that, we find our resting moment, which we found to be where is it? Is that right? 837.0 inch kips. So we found that, and then we use that in some further calculations, and we find a nominal tensile stress. Our nominal tensile stress is going to be 104 KSI. And then we use that to find our allowable tensile stress. And so that is going to be 63.9, which is greater than, or sorry, tensile strength. I don't know if I said tensile strength before, but that is going to be 63.9, which is greater than our 59.7 value that we found earlier. So now we're going into our column design. We have our gross area is 2.70. Simply wrote that down to keep in mind for later calculations. Then we have our effective slenderness ratio. But before we do that, we have this value of K. Now that's a coefficient. It's again for our specific case. We have a fixed end fixed by that column or that beam up top and then fixed onto the ground. So that's why we use this value of K that is different than you might have used or someone else might have used. So then we found our buckling stress or strength, 186.64. But then we actually found our critical buckling stress, which is going to be the buckling, the stress that your beam can experience whenever it is, and anything after that will make it critically buckle, or I guess at this point and anything after it, it would make it buckle critically. And so we compare that to our compressive strength, or no, we compare that to our compressive stress, and we get 3.59 KSI, which is greater than our value over here of 46 KSI. Or sorry, that is greater than our value over here. And also, this is important to say, our compressive stress of 3.59 would also be less than our critical buckling stress of 41.49. Okay, so we have the hand calculations, we've explained them. I might have gone too fast for you whenever I was explaining them. If you have any questions or maybe there's something you want to look into further, please rewind, pause, anything you need to look at that again. I encourage strongly. And so now we're going to go into our hand calculation, or sorry, our Excel sheet, which are representative of our hand calculations, or which represent our hand calculations. So here we have our Excel sheet. So the Excel sheet kind of follows in the way that your eye would follow the page. It goes from loads present to beam details to connection details and calling details. Now I have an important note over here. The Excel can be reviewed alongside the hand calculations. Each table will reference a page on the hand calculations. So this Excel was made after doing all the hand calculations. And so I put a little note on the top of these tables to show where on those hand calcs you can look for how I got this in more detail. All of the details are interconnected. Loads goes into beams, which beams goes into connections, connections goes into columns, and then there's a little bit of columns goes into connections as well, and then beam goes into connections as well. The point I'm trying to make here is that this is all interconnected, and to show that, I'll do this. So let's say that the client wants to change a detail or a dimension on our plan. Instead of having the width of the panel be 16 feet, he realizes through studying, through looking, through researching, that all the cars are going to be compact cars that will be using these charging stations. So instead of 16, he wants to use something like 14 feet. So we can change that simply by putting in 14. And then as you just saw, all of these values have changed as well. Not all of them, but most of them, and maybe even some of them, have changed as well. And so we have these little checks right here where it says pass to show that these values that change have passed. Now, maybe we can go in the other way and say that our client wants to increase them from 16 feet, which it was originally, and now he wants to increase it to something like 20 feet. Now, it's important to note that some of these failed. These two failed. This one failed. These two still passed, which is good. But the important thing is that you know where that failed, so you know where to improve your design. So let's move this back to 16. And then that's all for this Excel. If you want to look at it, you have the file in the Google Drive, so you can easily find it in there. So finally, we have our intercalc file. So as you can see, we have two files. We have our steel column and our steel beam. So let's look at the steel beam first. So here we have our steel beam. Here we have it. It's a W10 by 26, as we described earlier. Here are loads present, and then I selected auto add beam weight. And as you can see, it passes in all of these. The deflection ratios are higher in this one than I think I calculated, but that is just what you get sometimes. As you can see, it's a fixed end connection, connections, and a 15-foot span. Now to move on to our column details. And on all these descriptions, I also added kind of a note. So the column details you can find on page 5 on the hand calculations. So here again we have our loads, all of these things, similar to what you did for your project as well, almost exactly probably. And we have a load, dead load, so this is actually has been divided between dead loads and live loads, and so you might notice that this dead load is higher than the dead load that we did for the beam. That's because this is factoring in that beam weight, and so it was an increase after factoring that dead weight of the beam. Well, of course it was an increase, it wouldn't be a decrease. So that concludes this. Same thing as the Excel, you have access to the file. I encourage you to look into it more in more detail. So that's all that I have for this presentation. Thank you for watching. Thank you for listening. Sorry it was so long, but that is my email on the screen right now. If you have any questions or concerns or feedback of any kind, please feel free to respond. Thank you.